Good evening, everyone. I am Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So we will be going over the concepts discussed in week 2. It will probably help you solve the assignments of both 1 and 2. So a brief overview of what we've learned so far. Static stability is the initial tendency of any system to go back to equilibrium when subjected to a disturbance. Then for an aircraft, if it's subjected to some angular displacement, some disturbance, the initial tendency for it to go back to its trim position, its equilibrium, is longitudinal static stability in terms of pitch. Aerodynamic center is the point about which the pitching moment, Cm, is independent of angle of attack. So the forces are presumed to act about a point called center of pressure, which varies during the course of the flight, varies with angle of attack. And it becomes inconvenient for us to perform analysis at a point that varies. So the point about which analysis is carried out is the aerodynamic center, where the pitching moment remains constant with angle of attack. When we transfer the forces from the center of pressure to the aerodynamic center, it comes with a moment. So the aerodynamic center would have the forces, the aerodynamic forces, the lift, drag, so forth, with a moment, which is the pitching moment. The equation for pitching moment coefficient Cm is Cm naught plus dCm by d alpha into alpha. And the condition required for longitudinal static stability is that the slope between Cm and alpha should be negative. So dCm by d alpha, Cm alpha should be negative. We also require that Cm naught, the y-intercept of that graph, should be positive in order to trim the aircraft at a positive angle of attack. We have discussed this in the previous lectures. So I had asked in the previous class, what can we do to ensure that Cm naught is positive? For a cambered airfoil, so for a cambered airfoil, we know that Cm versus alpha would be with a negative Cm naught, y-intercept would be negative. Would be with a negative Cm naught. So what are the techniques that are used to make the Cm naught positive? I had said that we would discuss this in the next class. Both the concepts have been discussed in the lectures by sir. Can anyone tell me anyone? To ensure Cm naught positive. There were two concepts discussed in the class and one was extensively discussed. And with the equations given on the screen, you should be able to tell me at least one. Okay, let's go to the wing contributions. The wing contribution towards Cm has this term and this term, where the first term in this big braces is the Cm naught component to contribution of wing. And similarly for tail, this is the contribution. So looking at these two terms, can anyone tell me what can be done to ensure a positive Cm naught? Anyone? It is less than 0. What can we do to ensure a positive Cm naught? Tail setting angle. Yes, one of the options is negative tail setting angle. If we have this component negative, that is IT, if it's negative tail setting angle, then we can have a positive Cm naught. What is the other way? There are two ways discussed by sir. The other way, so this CMAC wing, the CMAC wing for a symmetric airfoil is 0. It's 0 because the center of pressure for a symmetric airfoil and the AC, aerodynamic center, are located at the same point. So when we transfer the forces and moments, there will not be a moment. For a positively cambered airfoil, it is negative because the center of pressure. So we had discussed this in the previous class. This is the center of pressure and this is the AC. This one. So if the moment generated, the forces generated, the CP are transferred to AC, there is a negative moment, negative pitching moment, that is pitch down. So for a positively cambered airfoil, the CMAC wing is negative. So another way to get Cm naught for the entire aircraft positive is to ensure that this term is positive. Now this term is positive for reflex airfoils. Reflex airfoils they have an upward bend towards the end. So even for a zero angle of attack, there is a negative component of lift, which when transferred to the aerodynamic center produces a pitch up moment. So the CMAC at the aerodynamic center of the wing would be positive. So the two techniques to ensure that Cm naught positive are, one is this IT should be negative, tail setting angle should be negative. And the other way is to have reflex airfoil cross section for wings, which has, by virtue of its design, a positive CMAC. Okay, is that clear? These are the 2 points that I could find out. If anybody can come up with anything else, let me know. Okay, moving ahead. The contribution towards Cm, towards pitching moment by wing and tail are given here. They're the same formula that we discussed last time. The first component is the y-intercept Cm naught. The second component is the slope, similarly for tail. Neutral point, analogous to AC for a wing, is the point about which Cm alpha for the entire aircraft remains constant, is 0. So the pitching moment about the neutral point remains constant during the flight, does not change with angle of attack. The equation for neutral point was derived in, I think, week 1. This is the equation. And static margin is a quantitative measure of how stable your aircraft is. So positive static margin is a stable aircraft, negative is unstable aircraft. So if static margin is 0, it is neutrally stable because XCG and XNP are the same point. So the CG is located at the neutral point. That means the aircraft is neutrally stable. These are a few of the formulas that were used by Sir in the previous lectures. So the downwards components, due to the angle of attack at the wing, there are effects on the tail. So the velocity seen at the tail is different from the velocity seen at the wing. There is a downward component that due to the wingtip vortices that we discussed in the previous class, there is a downward velocity component and effective angle of attack is reduced at the tail. The velocity and the angle of attack are different at the tail than at the wing. So these epsilon naught and the slope give how the downwash affects the airflow at the tail. VH we have used in the formula for previous formula. So this VH is the ratio, that is ST upon S and LT upon C. ST is the area of the tail, S is the area of the wing. LT is the moment arm of the tail. So the forces are produced at the aerodynamic center of the tail, and the moment arm between the aerodynamic center and the CG is represented by LT. C bar is the mean chord of the wing. This is one new topic that Sir mentioned in the previous lecture in week 2. So we have studied the CL alpha variation of a airfoil, that is CL alpha 2D. When we convert it to 3D, there are several effects that come into play. Like one of the effects that we discussed last class was the wingtip vortices. So when you have an infinite wing, so this is an airfoil. So airfoil is considered as an infinite wing. This is we discussed while discussing the aspect ratio problem. So if it is finite length, so if it's like this, the airflow from below the surface of the wing and the upper surface of the wing, they interact at the boundary. And due to that, there are vortices generated. And so there will be effects. The CL alpha of the 2D airfoil will not be same as the 3D wing. So this is the equation that tells you how the CL alpha of the airfoil is related to the wing. Now, these were a few questions that came up in the forum. I'll try to address a few of them. One of the questions was, why is CMAC negative? I had discussed this in the beginning of the class. I'll just go over it again. So if this is your airfoil, if it's a cambered airfoil, this is the location of center of pressure where all the forces are presumed to act. All the aerodynamic forces, that is lift and drag, are presumed to act. But since this CP varies with angle of attack, we have chosen an aerodynamic center. So aerodynamic center, which remains constant with angle of attack. And while transferring these forces to the aerodynamic center, it comes with a negative moment. Pitch down is negative. So when the CP is after the AC, it comes with a negative pitch down moment, which is why CMAC is negative. And the way to make this positive is to have the reflex airfoil. And for a symmetric airfoil, this CP and AC are the same point. So there will be no momentum and hence there will be no CMAC. Next question that was asked is how can lift act downwards? So the reference video that was put up with this question was, it dealt with the wing tail configuration. So what was mentioned was the wing is at a positive, this is the wing, and the tail was at a negative angle of attack. Bear with my drawing. So what happens here? The negative angle of attack, effective negative angle of attack, the summation of forces in the vertical direction would be in the downward direction, right? So the forces that are acting in the upward direction are lesser than the forces that are acting in the downward direction. So the sum of the forces would be downwards. So it doesn't mean that the lift on the wing is negative. So the question asked was, if the lift on the wing is negative, then the aircraft would just fall down. But Sir was discussing this with respect to tail, and he mentioned that due to the negative tail setting angle, this lift generated would be the effective, the total forces would be downwards and would produce a pitch up moment here at the CG. Next question was, what are the effective control surfaces on aerodynamic forces? So if this is your tail and this is your elevator, deflecting this elevator down, it produces an increased lift. There is a delta CL, delta L, which is positive. So with deflection, downward deflection of elevator, that is positive deflection of elevator, there is an increase in lift. Similarly, there would be an increase in drag also. This was the question asked, does it contribute to only lift or drag also? It contributes to both, even drag is increased, but since it's a small surface, it's negligible and we are not considering it during the derivations. Next question was canard plus tail. So the question was, if the wing is symmetric and there is no contribution of wing towards stability, that is if the aerodynamic center of the wing coincides with CG, in such a case, there will be no contribution of the wing towards stability. Right, so the equation that we have, wing contribution, this is the contribution towards stability. If the aerodynamic center of the wing coincides with the CG, there will be no contribution of wing towards stability. So the question asked was, if there is a canard, canard is a surface that is similar to a wing that is ahead of the wing. So what will be the stability of such a configuration? Now we know the contribution of the tail towards stability, alpha tail, is what? Eta VH CL alpha tail 1 minus into, what was the term here? Okay, that term is included here. So a similar term would come for canard. So CL alpha C would be a similar thing. This must be for canard. And here you would have SC by S. This VH is ST by S into LT by C. So similarly, we have here C. And so the downwash component acts on the tail due to the after effects of the airflow over the wing. There will be no downwash effect on the canard. So if we ignore the downwash effects on the tail, then these two terms, if all other geometric parameters are same, it may cancel out. But due to the effect of this downwash on the wing, this term, even if all the other components are same, even if all the other aerodynamic and geometric parameters are same, will have this component 1 minus dou epsilon by dou alpha due to downwash. So it will not cancel out, and the effect of the canard will be more as compared to the tail. And canard, by virtue of it being located ahead of the CG, has a destabilizing effect. Is this clear? So the overall effect, I believe, would be destabilizing due to the incorporation of this downwash effect on the tail. Is it clear? Can somebody confirm? The question was, if the wing has no effect on the stability of the overall aircraft, what would be the contribution of canard and tail? Okay. So that was it. Another question that So another question that is there in your assignment deals with the low wing, high wing configurations. I'm not going to completely discuss this, but I'll give you a clue as to how you can proceed with it. So we have derived the equation considering the wing and the CG, the wing AC and the CG on the same line. This was the AC and this was the CG. Now, if we have a low wing configuration, this would be the wing AC. And the aerodynamic forces would be acting here, drag and lift. Similarly, if we have a high wing, this would be the AC. So this would be where the lift and the drag act. So using these, there will be a ZCG. So till now, we were only looking at the X component of the distance between AC and CG. In the low wing and high wing configurations, you would have a Z component. So the CG would be located either above or below the wing AC. So using this, if you perform the derivation again, you should be able to answer one of the questions in the assignment. Okay. So this was a question that was asked in the previous session where I had written. So do you remember this question where we had to find the CL at trim, and this was the equation used, and I had asked how we derive this equation, and this is what I had written. So it is CM is equal to CM naught plus CM alpha into alpha, and the CM alpha is nothing but DCM by DCL into CL alpha. And I had said that this CL alpha into alpha was CL, and someone had asked me how that would work, because we know the equation of CL is CL naught plus CL alpha into alpha. Now, this CL naught is CL at alpha equal to 0. Okay, so actually what this should have been, there should have been an extra minus DCM by DCL into CL naught. Because here CL alpha into alpha would be CL minus CL naught. Okay, and the CL naught is CL at 0 angle of attack. Now, when we continue with this derivation, you get the CM naught. The CM naught is CM at 0 angle of attack plus minus DCM by DCL CL naught plus DCM by DCL into CL. Now, this entire term is the CM naught in this equation. Okay, this CM naught is CM at lift equal to 0. Okay, is that clear? This CM naught is the CM naught at alpha equal to 0, and this is at lift equal to 0. I'm not sure who asked me that question, but is it clear now? Can you hear me? Okay, so is this a derivation of the equation clear now? The two CM naughts are different. One is CM naught at 0 angle of attack. So this CM naught is at 0 angle of attack, and this CM naught is at 0 lift. It will be same for a symmetric airfoil, but for cambered airfoils, it will not be the same thing. Okay. These are the new topics that were discussed in week 2. So what do control surfaces do? Control surfaces, okay. Control surfaces are brought in so that we can fly our aircraft at different CL trims. So we know this graph, CM versus CL. This is the traditional graph for CM versus CL. And at trim, this is the CL trim. Trim is when all summation of all forces and moments are 0. So in this case, CM 0 would correspond to trim. Now, if we wish to fly at a different CL trim, that is at a different velocity, suppose we want to fly at a greater velocity, the CL required would be greater. For a lesser velocity, the CL required would be greater. So if we have to fly at this CL and trim the aircraft at that CL, we require control surfaces. So control surfaces were brought in to enable us to trim the aircraft at different velocities. Okay. So what it effectively does is it translates this graph. It doesn't rotate it. So does the CM not change? Does the CM not change when we deflect a control surface? Yes. Does the CM alpha change? Does the slope change? No. So I believe one of your questions in the assignment says the deflection of control surfaces, in this case elevator, what is its contribution towards stability? The contribution towards stability is the slope. So you should be able to answer that question now. So one convention that we follow in this course is the elevator down is considered positive. So when we deflect the elevator down, it produces additional lift on the tail. That is considered positive. That's the convention. CL delta E, CM delta E, these are the two equations derived in the lectures. CL delta E is positive because each of these terms is positive. CL alpha T, the slope, lift curve slope for a tail is positive. This tau, control surface effectiveness parameter, is positive, and everything else is positive. So CL delta E is positive. Similarly, for CM delta E, all these individual components are again positive, but it has a negative sign. So this CM delta E is negative. The delta E trim required to trim an aircraft at the given CL trim, this is the equation that is followed. So we also have delta E trim, delta E naught plus d delta E by d CL at trim into CL trim. So this d delta E naught is this component. CM naught is positive, CM delta E is negative. So this entire term would be positive, right? CM naught is always positive. We have to ensure that to trim the aircraft at a positive angle of attack. And CM delta E, we've seen, is always negative. So this delta E naught would be positive. Similarly, what would the slope be? D delta E by DCL, this value. What would the sign be? This XNP minus XCG, what would the sign be for a stable aircraft? XNP minus XCG is the static margin. Static margin for a stable aircraft, would it be negative? The XNP minus XCG is the static margin. So the XNP minus XCG, that term is positive, and CM delta E is again negative. So the slope would be negative. So the graph between delta E and CL would be like this. Is this correct? Do you agree with me? This is delta E naught, positive delta E naught, and a negative slope. Does this seem right? Yes, we have a negative slope. The XNP minus XCG is positive, CM delta E is negative. So the slope D delta E by DCL at trim is negative. So the slope would be negative and a positive y-intercept. Now, what happens when the CG is at neutral point? How would the graph be? When the CG is equal to the neutral point, this term would vanish. So the entire slope would vanish. So what it means is delta E trim will remain constant. Delta E trim will remain constant. This would be the line when CG equal to NP. So as the CG moves towards NP, the slope keeps reducing until it becomes 0. Okay? The delta E naught will remain same. I'll just erase that last line. So delta E naught will remain same, but the slope will keep changing as the CG moves towards NP. So this is CG1, CG2, CG3, and this is CG1, 2, 3, and this is the neutral point. As the CG moves towards the neutral point, the slope of this curve keeps reducing until it becomes constant, until it becomes 0. Okay? So these are the few concepts that we studied in week 2. We'll begin with the questions. In an aircraft, without changing any other dimensions, the distance of the aerodynamic center of the tail, ACT, from CG of the aircraft is increased. Due to this, the change in longitudinal stability of the aircraft will. So what it says is, if this is the fuselage reference line, the AC of tail and CG. If this distance is increased, what will the contribution towards stability be? Will the stability increase or decrease? Increase. Yes, increase is right. So increase, yes, increase is right. This is the larger the moment arm, larger is the moment produced on the CG. Larger is the restoring moment produced at the CG. So when this distance increases, the moment arm increases and the total pitching moment at CG due to the tail increases. So as the distance increases, the longitudinal stability will increase for the given aircraft. Yeah, so this is the equation where this term, this XACT minus XCG, if it increases, we know this negative component increases. More negative the slope, more stable the aircraft. If the distance between the aerodynamic center of the tail and the CG of the aircraft is reduced by 10%, what will the new area ratio in order to maintain the same volume ratio be? Okay, just ignore that 0.7. In order to maintain the same volume ratio, just ignore this. How do we proceed with this question? Can somebody tell me the first, like how do we start? Somebody unmute and speak. We just discussed in the previous question the equation. So what relates the area ratio to the volume ratio? What is the equation that relates that? So this equation, this VH is the volume ratio, this ST upon S is the area ratio. This is the equation that we will be using in the next question. Okay. So let's write this. So the original VH, so VH old is ST upon S old into this is nothing but LT. The XACT minus XCG we have represented as LT. And when you divide it by the chord, you get a bar over it. So LT old. What it says is this LT is reduced by 10%. So your VH new would be ST upon S new into LT mu. This LT mu is less by 10%. So that would be ST upon S mu into 0.9 old. Now, in order to maintain the same VH is what they have said. So VH old equals VH new. So when we equate these two, this term and this term, what do we find? How is the relationship between both of them? VH old is ST upon S old into LT bar old is equal to ST upon S new into 0.9 LT old. So what is the relation? What is the correct option? How is the area ratio of the old configuration related to the new one? All the values are here. Just which option is correct? Third. Okay. Third. Just verify. Right, okay. During a flight, if the elevator is deflected with a certain positive angle, how will this affect the stability of the aircraft? We just discussed this. Can someone tell me the correct answer? So your elevator here, it's deflected positive means it's deflected downwards. What will its effect be on the stability? Are you sure it will increase? During a flight, if the elevator is deflected with a certain positive angle, how will it affect the stability? So we just discussed. Anybody else wants to try? We just discussed that the control surface's purpose is to CM and CL. To trim it at a different CL, we need to move the slope, move this line. There is no change in the slope. There is only change in the CM naught value. So if there is no change in the slope, if DCM by DCL remains constant, the stability will remain constant. So there is no effect of the control surface on the stability of the aircraft. We just discussed this in the first slide. So here, okay. So the answer will be, what will the answer be? If we deflect the elevator down, how will the stability of the aircraft change? How will the stability of the aircraft change? Will it change? I'm not going to answer this question. I have mentioned this a couple of times. Yes, it remains unchanged, correct. With increase in static stability of the airplane, the elevator required for a given CL trim will be. So for a particular configuration, there is a elevator delta E trim required to trim the aircraft at a given CL trim. For the same CL trim with an increase in static stability, how will that elevator trim change? Delta E trim, how will it change? Can anyone try to answer this? For the same CL trim, if we wish to trim the aircraft at the same CL, but with increased stability, what would the change in elevator deflection angle be? Unchanged. So how did you come to the unchanged conclusion? There is, okay, so it works that way. So if there is no change, if with deflection of elevator, there is no change in the stability, but it doesn't mean that change in stability does not mean that we will have to use the same delta E to trim the aircraft at the same CL, right? Okay. For this question, what would the answer be? Can anyone try to answer this? With increase in stability, and if you want to trim the aircraft at the same CL, the delta E trim required, would it be more? Would it be less? Would it be same? What is the equation to trim? How do you find out the delta E to trim the aircraft at given CL trim? Yes, okay, let's just look into it. The equation to trim is this. Delta E trim is delta E naught, which is minus CM naught by CM delta E, plus this X bar NP minus X bar CG, which is your static margin, by CM delta E in CL trim. This is the equation that we discussed to discuss this slope. By CL. So now, increase in static stability. What does that mean? Which of these terms will change when we say increase in static stability? Will anything change in this term? CM naught, CM delta E, will it change with an increase in static stability? Will this term change with increase in static stability? Will this term change with an increase in static? What is static stability of a airplane? Longitudinal static stability. It is this. It is measured by this quantity, right? This is the static margin. Static margin, I told you, was a measure of the stability of the aircraft. So this term will increase with an increase in stability, correct? this intercept of the equation remains same. The slope here changes with an increase in static margin. So what happens here? I told you when the CG moves towards NP, the slope reduces until it becomes this. When the CG moves away, so when XNP minus XCG is greater, when the CG moves away from neutral point, the slope increases, right? So it becomes like this. So this is the term that changes with change in stability. So now can you tell me this delta E trim required to trim the aircraft at the same CL? For the first case, suppose it's 10. 10 is a huge number, but I'm just telling you 10. For the next case, when this value is increased, will it be more than 10 or less than 10? For the same CL trim, this value is increased. Will delta E trim be more or less? This term also remains unchanged. Yes, somebody was saying something. More, yeah. So the answer would be more. So for the same CL trim, to trim the aircraft at the same CL, a more stable aircraft requires more delta E trim. This is analogous to one of the questions that we discussed in the previous previous tutorial, the last question, I believe. If it's more stable, it is less maneuverable. So we require more control surface deflection to maneuver the aircraft. Right, so is it clear now? That previous question, the maneuverability and stability are opposite of each other. Right, so more stable the aircraft, more delta E trim required to trim the aircraft at the same CL. So it's difficult to maneuver. Okay, can we go ahead? Is this question clear? So we'll just quickly go over this question that sir had discussed in the class, because I believe it's very essential for you to solve any other question. So what is given to us is the CM, the pitching moment coefficient effect of the combined effect of wing and fuselage. So we have a negative CM naught and negative CM alpha. So the aircraft is stable, but you cannot have a negative CM naught because we need to trim the aircraft at positive angle of attack. So though the aircraft is stable, we need to change this parameter. So all the other parameters are given. So let's try to solve the questions. It is desired to have the complete airplane pitching moment characteristic as this. So here we have a positive CM naught and negative CM alpha. Right, so this is a stable aircraft that can be trimmed at a positive angle of attack. If it's just the wing and fuselage contribution, then that is not possible. So now what is the contribution of horizontal tail to CM naught? This is the equation, right? Right? Can somebody tell me the value? CM naught tail. Contribution of tail towards the CM naught, towards the intercept. Can somebody tell me the value? All the values are given in the question. So this is minus 0.05 is the CM naught of wing and fuselage, and 0.15 is the contribution of tail, of the wing, tail, and fuselage. So what is the difference between those two? This value is 0.15 and this value is 0.05. What is the value? 0.2, right? Okay. Moving on. 0.2. Similarly, what would the contribution towards CM alpha of the tail be? This is CM naught of tail. What is the contribution of CM alpha? Contribution to CM alpha by the tail. That is this component. So CM alpha tail would be CM alpha of wing, fuselage, and tail minus CM alpha of tail. Of wing and fuselage. What is this value? CM alpha of wing, fuselage, and tail. What is the value? Of wing, fuselage, and tail. Okay, you've given the final answer. Okay, okay. So that is the next question. Just here would be minus 0.0035 minus wing. Okay, specific. What is the value? Minus 0.25. Final value would be, he has given the answer. Minus, okay, that's correct. Next question, the approximate value of dou epsilon by dou alpha, which is the downwash angles component, slope. Okay, so what would the value be? 0.35. Let's just find it out. 2 into CL alpha wing is, where is the CL alpha wing? CL alpha wing. Okay, so CL alpha wing, we'll have to alpha wing is given as 0.07, 0.07, and pi. E is given as 1. It's 1. To aspect ratio of the wing, this should be wing aspect ratio. So what is aspect ratio of the wing? 7.3. Okay, so this will give you the final answer as here your CL alpha is given in per degree. Okay, you need to convert it into per radian. So 57.3. Final answer is yes, 0.35. Thank you for finding out that mistake. 7.3. So final answer is 0.35. Okay. So next question is, what is the tail volume ratio? So equation is given here. We have CM alpha tail. What is VH? Tail volume ratio VH. Somebody answered. CM alpha wing. CM alpha wing is minus 0.0035. Where did I make a mistake? Yeah, so it would be minus of minus. Right? So this is the CM alpha of wing, tail, and fuselage. This would be minus of minus 0.0035. Is it clear now? Yeah. Yeah, so tail volume ratio. What is the value? So VH, CM alpha tail by eta CL alpha tail 1 minus dou epsilon by dou alpha. So what is CM alpha tail? What is the value we got? Minus 0.0215. That's the right answer, I think. Tail efficiency factor is 1. CL alpha tail is 0.073. And we have 1 minus dou epsilon by, we found this in the previous question, 0.35. So what is the VH? Can somebody quickly find out this value? Yeah, 0.453, correct. Next question is, what is the ratio of horizontal tail area to wing area? We'll use the equation that we have been using. So VH we know as 0.453 is ST upon S into LT is given as 4.496 by mean chord of the wing. Where is the wing chord? What is the ST upon S value? Can somebody calculate and tell me the answer? ST upon S, 0.453 into 1.524 by 4.496. It comes to 0.022 radians. Sorry. What is the value? What is the value? Point 153. Okay. Next is the approximate value of epsilon naught. Epsilon naught is the constant downward angle, downwash angle component on the lift. So this is the formula for that. 2 into CL naught. CL naught of the wing. CL at alpha equal to 0. This one. 0.26 by pi. E is taken as 1. And AR aspect ratio is 7.3. So calculate this value. This is 0.022 radian and convert it to degrees to get 1.3. Okay. This is just a repeat of what sir had done. I just think we should go over it. Now the tail incidence angle. So we have all the terms in this equation. We have VH, we calculated VH, eta is taken as 1, CL alpha tail is given directly in per degrees. We have I wing in degrees. We have epsilon naught, we just calculated it. We need to find out this tail setting angle. So tail setting angle would be C naught of tail, right, by VH eta CL alpha tail should have a negative sign, plus I wing plus epsilon naught. So can you calculate this value? Is this equation correct for IT? Can somebody verify if the equation is correct for tail setting angle? Is it minus? No, it will be plus. So it's correct, right? So what is the value IT? What is the value of IT from this equation? If the equation is correct. Minus 2.7, is that right? Yeah, okay, minus 2.7. Okay. So now we'll start with another question. So this is the data given to you. The weight is given, cruise velocity is given, the area of the wing, the cruise altitude, the density of the cruise altitude, the aspect ratio, the XCG, XAC, which coincide in this case, neutral point location, and all the other parameters of the wing and tail are given. Okay, so the first question is, what is the lift coefficient for cruise? What is the formula that we follow to find out lift coefficient at cruise? This we are studying in performance. Can you quickly tell me? Lift coefficient at cruise. It's the basic formula which is studied in performance. What is lift? Lift is equal to dynamic pressure into CL, right? What is the lift equation? This is the lift equation, right? At cruise, lift equal to weight. So we can take this as weight. So weight equal to half rho V square SCL, trim. Trim in this case, cruise is considered to be trim, okay? So that CL would be 2 into weight by rho V square S. That is 2 into 2500. and that is in kgs, so 9.81. Density is 0.85 into 1 square into 60. Can somebody calculate this value? Point 0.5, so 0.569. Okay. So it's the third answer. 0.569. Okay. Next question is calculate the downwash angle at tail in degrees. We just use this formula. Can someone tell me what would the formula be or what the final answer would be? We just used the epsilon naught formula in the previous question. Epsilon naught is equal to, right? So we have 2 into CL naught. Okay, it's there. How do we find out this CL naught with the given data? Can someone tell me how to find the CL naught with the given data? Okay, so we have the lift curve slope is given to us, right? Lift curve slope is not given, but we have this value. There, see? So alpha at 0, alpha that produces 0 lift is -2. So this is -2 degrees. And we have the CL alpha. CL alpha is the slope. CL alpha is 4.8584 per radian. And we have alpha that produces 0 lift. 0 lift. Can someone tell me what is CL naught now? CL naught of the wing. We have this point. We need to find out this. This is CL naught, right? That is CL naught. Does everybody agree? That the point that I've marked is CL naught. Is that correct? The point on the graph that I've marked is at CL naught. Is that correct? Yes. Okay. So how do you find out CL naught? How do you find out CL naught? It's 4.584. That is the slope into the angle, right? Into -2. But -2 is in degrees, right? So what do? Divide 57 or 57.3 or multiply? Is this correct? Is this how you find out CL naught? Okay. So what is the value? 0.16. So this is CL naught, which we'll use in this equation. So what is epsilon naught now? 2 into 0.16 by pi. E is given as 1. Aspect ratio of the wing is 5. What is this value? Zero point 0.02 radians. So converted to degrees, how much will we get? 1.16 degrees, right? So the next question, calculate the value of CM naught of the aircraft, CM naught of the entire aircraft. So what do? CM naught of the entire aircraft is the combination of CM naught of tail, fuselage and wing. You've assumed fuselage contribution to be 0 now. So the CM naught of the entire aircraft would be the contribution by wing and tail. So what is the CM naught contribution of the wing? We had discussed right at the beginning of the class. So these are the two equations, right? CM naught contribution by wing, CM naught contribution by tail. CMAC wing is what? It's given to us. 0.45. Eta is assumed to be 1. CL alpha tail 4.584 and into I wing wing setting angle 3 plus epsilon naught. Epsilon naught we just calculated previously. We'll take the value in degree, that is 1.16. 1.16 and tail setting angle 2, and we need to convert degrees into radians. Right? Am I doing this right? Okay, I'm not sure for what you've given this answer. Minus 0.1 is for what? Minus 0.1? Okay, let's just continue with this thing. Into 1 upon 57.3. Okay, what is this value? What is this value? 0.45 into 4.584 into this entire angle in degree, and we convert it to radians by dividing by 57.3. So what is this value? Comes to 0.1774. So the overall contribution, that is Cm naught, is Cm naught of wing plus Cm naught of tail, which is minus 0.1 plus 0.1774. What is this value? 0.0774. Right? So this is the correct answer. Next is a value of Cm delta E. What is the equation for Cm delta E? 0.22. Who said 0.22? For what was it? Okay, I think it's the previous answer. Okay, let's just continue with the Cm delta E. Cm delta E, what was the equation? Does anyone remember? I put it up in the beginning of the slides. Cm delta E, the negative value. So this is the equation for Cm delta E, where eta is assumed to be 1, VH is 0.45, CL alpha tail is 4.584, and tau. Tau is the control surface effectiveness parameter. That is 0.4. This is fairly simple. What is the answer? Minus 0.66. Okay. Static margin during cruise is close to. Static margin is. What is the equation for static margin? Simple equation. Static margin is the difference between two positions. What are the two positions? Static margin is XNP, X bar NP minus X bar CG. Right? So X bar NP is given as 0.52. X bar CG and X bar AC is the same, which is 0.3. What is this value? Am I audible? Are you listening to me? Am I audible? Okay. So this value is 0.22. Next, for cruise flight, delta E required to trim the aircraft is approximately. So delta E trim, to trim the aircraft at some CL trim, we have seen that equation previously. This is that equation. In this equation, we have Cm naught. We've calculated Cm naught. We've calculated Cm delta E, Cm delta E. X bar NP minus X bar CG is the static margin we just calculated. The CL trim is the CL trim is CL at cruise. It's the first thing we calculated. Okay, so you have every term here. So what is delta E trim? Substitute all the values and somebody tell me the answer. Cm naught we calculated to be Cm naught was 0.0774. Cm delta E was minus 0.66 plus X bar NP minus X bar CG we just calculated 0.22 minus 0.66. And what was the first answer? CL trim was 0.569. So what is the value here? Just quickly calculate this value. Comes to minus 0.0723 radians, which is approximately converted to degrees. What is the value in degrees? Multiply by 57.3. What is the value? Minus 4.143 degrees. Is this question clear to everyone? All of this series of questions, is it clear? Is there any question in these series of questions? From here, the CL, we know how to calculate the CL. We calculated the downwash angle at the tail. We calculated Cm naught of the entire aircraft, contribution from wing and tail separately. We calculated Cm delta E, then the static margin, and finally the delta E required to trim the aircraft at cruise velocity. Okay, is this clear? Okay. Which of the following correctly describes this term delta alpha T by delta E? This term we have used in these equations. What is this term represented by? Is it elevator effectiveness? Is it elevator effectiveness delta alpha T by delta E? This is the term we refer to as tau, right? That is the elevator effectiveness parameter, right? So it is the elevator effectiveness parameter. The change in effective angle of attack of horizontal tail due to elevated deflection. Yes, that is delta alpha T by delta E. For a typical aircraft, its value is around the range of 0.4 to 0.5. Sir had mentioned a graph. So its value is around 0.4 to 0.5, right? This was tau, and this was the area ratio. So this is the value, this is correct, and it is represented by tau. So the correct option is A, B, C, and D. Okay. With this, the questions are over. Does anyone have any doubts? Is there any formula or relation relating CG, AC, neutral point? So I believe this is for one of the questions in your assignment. We can discuss this after the assignment due date is over. Okay, I don't think you need a formula to answer that question. Using the options that are given, you should be able to figure it out. Is it okay if we discuss after the assignment? Due date is tomorrow, right? So next class we can discuss this. Okay, but you should be able to answer it without a formula is what I believe. We'll discuss it in the next class. Any other questions? Any other questions from today's tutorial? No. So I will share the YouTube playlist. You can watch the recorded videos there later. So I've put the link of the previous recording. In the same playlist, the recording of this week will be uploaded. So you can watch it whenever you have time. And we can discuss the doubts in the next session. Shall we end this meeting? Sorry? Okay, I hope there are no other questions. Have a very good evening. Thank you.